Okay, let's get started. Yeah. So let's get started. Talking with some of you during the hands-on session and realized there were some things that maybe are not clear enough, and then also going over notes. My notes, I probably went a bit too fast in some derivation. So let me just go back to trying to explain a little bit more again the rho and the discretization philosophy that goes into things, just to remove any possible doubt. So let's imagine, again, having a continuous function, and this function is being governed, the evolution, maybe this is at any given initial time, I want to know what happens at later time, either by an equation that looks like so. We are always thinking that we have hyperbolic problems, and hyperbolic problems that have sufficiently nice properties, we argue we can diagonalize, and then once we go into diagonal form, we could recognize variables where we just have a set of advection equations, let's say. We're oversimplifying, but at the bottom line, this is a building block that we're having in the back of our minds. So if we have an equation for any given variable that obeys something like this, u comma t equal lambda, where this lambda does not depend on the variable itself, then we are in this regime where we call linearly degenerate, or where importantly shocks cannot arise. If we have a smooth enough initial data, at least for a period of time, it's not going to develop arbitrarily large gradients. If instead this lambda depends on the function itself, on the variable itself that we're trying to iterate, then this one will generically give rise to very high gradients. So our approach to this equation and that equation will have to react that, or we're going to have severe problems. So this one is actually the easiest one. Pretty much any discretization strategy works well, because smooth initial data would, by and large, remain smooth, or smooth enough that we can use all sort of different recipes. And so the one that you discussed with Sasha was the finite differencing. So this function is represented by discrete points that take values associated to discrete points in a given grid. So if someone says, I want to study this particular initial data, thinking of what would be the initial data once we go into the discrete level is just simply asking, what are the values of the function at those discrete points in the grid? That would be our discrete representation of the function. And then we go on with the techniques that Sasha described. And of course, even fancier techniques depending on the problem you're working on. The finite volumes, on the other hand, begin by saying, oh, we have this issue, we need to deal with it. We know discontinuities will arise, so how are you going to address this? So we argue the best way, and we're going to go back to that, was to think of it as a sequence of Riemann problems. And so it becomes more convenient not to think of values of functions at point, but average of functions in cells. And then at the interface of each cell, we're going to solve a Riemann problem either exactly or approximately. And so rather than thinking of now the function of having these values at discrete points, we think we have these average values in these cells. So each degree, this is composed or decomposed in terms of cells. Of course, it's always too tempting to think, oh, it's the boundary between these 2 points. And that's perfectly fine, it's consistent, but don't get lost. The main thing is not what happens here, but the average in the cells. So this function continues, which in this approach is seen as a sequence of points. And as we take the discretization length to 0, then we fill up all the points in between and recover this. Here we are saying we have a whole bunch of average in these cells, and if we take the length or the surface of the cell to 0, to the volume of the cells to 0, then we're also going to recover the continuous function, right? It's just a different representation. If someone hands us this function and say, well, let's try to find the solution to the future of it numerically, we need to first define initial data, while here we're just evaluating the value of the function at the discrete points. In here, what we're going to have to do is just compute at the very beginning just the average in the cells. So we're going to have an integral between the point I and the point I plus 1, which are the boundaries of the cell, of the function iterated that gives us the average of the function in, say, this cell that is here. From there on, we move on with a discrete strategy. So there is this extra step in here, but we have to recognize that in some sense that step was there. The evaluation at discrete points was what was involved in the discrete representation of the function here. In this case, it's the average or the iteration per cell is what is involved in getting a discrete representation of the function in this approach. Of course, everything we see, this is the most complex case. Everything we say that is applicable to equations that satisfy, or the systems that have this type of equations, the techniques we derive for those will also be applicable to these ones. Because if we can deal with a very hard, complicated problem that is associated with sharp discontinuities, we obviously will be doing a good job if the solution is smooth and it remains smooth. But as you'll see today, the amount of work that is going to be associated with this is significantly higher. So your implementation will be degraded in efficiency. So when you can get away with this one, life becomes much simpler. But if you know you can get here, you have to follow this route. So once we said, well, let's go in that direction, all this is in the notes. So just, I don't think you need to write anything. Just pay attention. If there is any question, just ask me. So let's imagine we have a problem of that type where discontinuities or sharp gradients will arise. Now we have in our mindset that we're really working with averages in our averages. So if that's my cell, I'm going to call that cell the I cell. Let's say this is the I plus 1 cell. And the boundary between the I cell and the I plus 1 cell, I'm going to just assign label I plus 1/2 because it's in between these two. Similarly, the boundary to the left, I'm going to assign the label I minus 1/2 because the self boundary will be in between cell I minus 1 and I. So now we need a recipe to iterate this equation. We're assuming, say, that we have this equation, q comma t, some function of q, this is a nonlinear function equal to 0. So at least pictorially, we're going to say, well, the straightest and simplest possible discretization consistent with our equation should be, well, the average value of the function, the variable q in cell I at time n plus 1, so here, it's going to be the same at the previous level, minus delta t, divided delta x being the distance between the two boundaries, times the flux going through the boundary at the right and the boundary on the left. So now what we have to do is give a prescription for these. We don't need a prescription for this anymore. We know what these are. We're going to be carrying all through. Our variables will be the cell averages. So quickly we're going to be dropping the idea or saying everything. Oh, Q is the average value in a cell because that's what we're using. Finite value of finite volume representation. Every time we think of a variable, we're going to think this is the average in this cell. So we now need a prescription to calculate those fluxes, and that prescription has to be mindful that we're solving a Riemann problem, therefore we're considering the possibility that the average here and the average there might be discontinuous. So we have to react to that. And whether it is continuous, I mean, lower to higher or higher to lower, we're going to have to do different things. And by recognizing which way the possible, say, discontinuity is moving even to the right or to the left, we're going to have to react to that. So that we need a prescription that takes that all into account. So Roy, and we're going to go again quickly through the main things, provide an idea for us, which was, well, we want to approximate that flux in a way that we can work in a linear form. So we're going to say, well, this f of q, whatever q would be, which by a hat, I'm now saying whatever we're going to be evaluating that cell interface might have, it's going to be given by a matrix times the value that q hat we have there. And our task will be to define this A and these q hats in the right way that they capture what the true flux is doing at that point. And the physical pathologies or issues that we're going to have to deal with when we think about possible discontinuities. So Roy tells us, well, the flux, say, it's 1/2. This is the flux evaluated with information primarily to the cell on the left of that interface, the flux evaluated with information primarily from right of that cell, minus the sum over all eigenvalues of this matrix A, the absolute value, times alpha. Alpha is the jump between what happens at the left and the right, and we're going to go back to that. And E is the right eigenvector, so there what I call is R. So let me just call it R. So now let's go again through what are the steps there. So assuming we have this matrix, which again we're going to have to say what it is as we talk about different problems. Assuming we have this matrix, any variable we have, because we assume that this matrix has a complete set of eigenvectors, we can always write any variable in terms of these eigenvectors. So Q bar I, which is the value of our variable in the left side, or a set of variables in the left cell, the I cell, is the sum over some coefficients, which we're going to have to determine, times the eigenvectors. Of course, we know the eigenvectors. We can get those coefficients by inner product. So just a standard calculation in linear algebra. We can do exactly the same thing on the right, the cell to the right of our interface. And so that, because we're assuming that our matrix has eigenvectors, right eigenvectors given by das R and eigenvalues lambda p, we can always do this. That, then the inner product would allow us to determine B, beta, and gamma. Out of the beta and gamma, we can compute the difference, and that's already telling us about the jump across the interface. Now what we say is, we'll do one more step, or one more observation, is that we can write this Q hat, the approximate value that we have at that cell, as using quantities from the cell I, that would be equal to this Qi plus the sum over the negative eigenvalues times alpha p, this jump, or p. So this is already telling us, well, given that we know the eigenvalues, this p solution is being determined from the left cell, from the left side of the cell, and knows about the jump. But this we can also do from the right side of the cell, and it's the same. So the prescription is, okay, take the average of these two. That's what we're going to call Q hat, and that's going to be 1/2 Qi plus 1, plus this 1/2. One is contributing the sum over negative eigenvalues, the other one over the positive eigenvalues, alpha rp. But that's Q hat. What we needed, and this is what the step I went too fast the other day, what we needed was F. But the prescription is, if we act with the matrix on Q, that's the approximation of F. So the last step is to now act with the matrix on Q. So A times Q, when A multiplies the Q's, gives me the fluxes. But when A multiplies the R, gives me lambda rp. And because of the signs, that's when I'm mindful of the sign and take the absolute value and change one of them to a plus. So that's the final expression. And this is all I have to work to compute the flux at the right cell. And of course, the same goes through on the left cell. So it's complicated, it's rather annoying, but if we do it very modular, okay, we can just sweep through boundary by computing everything. Everything here is explicit. So if I know everything at the level n, I can compute every blocks and then just take the step. We can try slowly to be better than that. And one thing we could do is just, rather than using these Qs, which are the cell values here and there, which is the evaluate things slightly closer to that cell. The ideal, or the analog thing would be just try to put as fine a resolution as you can so that this cell shrinks. And if it shrinks enough, then eventually you're doing an excellent job, because there's too little distance between, say, the middle of the cell and the boundary. Once we're taking an average, we always do a better approximation at the center of the cell than we're doing at the right of or left of the cell. So here we're just trying to help out a little bit our accuracy by extrapolating a little bit. So adding with this slope, we don't want to overshoot or undershoot, and this is where we have this mean mod, and this is how we can improve it a little bit. But if you don't do that, you're still going to have a reasonably good approximation, which is first order accurate. So if you go through the nodes, so that's added kind of as a reconstruction, so something you can add to your scheme. And there is also a comment about where you can try and do second order in time by using a two-step Runge-Kutta. That helps. And this is just kind of the first foray into trying to come up with methods that deal with all these physical issues that we know we're going to encounter, and then try to do better. Because this is a first order approximation, it's a first order everywhere. So suppose you have a solution where it's perfectly smooth everywhere, then it has a shock here or discontinuity and continues on perfectly smoothly. So then this approximation is such that it's first order all through. While in pieces where the solution is much smoother, we could try and gain higher accuracy and only lose it at very small subsets of our solution. Say again. Eventually here. So first we compute it formally, I'll show you an example, and then you do this. So of course you still don't have that one, but you can take this average, and that's where you're putting it. So if you open like what I mentioned last time, Levesque's book, they have tons there of schemes that are higher accuracy than this. And this higher accuracy is gained everywhere except in the very large gradient regions where you necessarily drop to first order. So any questions on that? Okay. So remember, even though you're very tempted to think of these points, when you're here, you have to think this way. These are cells that you're thinking about. Okay, one more thing before we move on. So the other day, when I wrote the special reducing hydrodynamic equations, in one of these equations, I had a d here. That's because I was thinking of the discrete derivative. But because I have a d variable, that could be confusing. So these are the equations of motion we obtained for special Tvc hydrodynamics. We recognize in them with a slight kind of interpretation that this is conservation of particles. But because we're talking about relativity, the concept of particles and the energy that each particle has is not as clean as in Newtonian, say Newtonian mechanics. So we have these variables that in the right limit recovers those values or that interpretation, but it's general for what the fluid might be doing. So we define this variable d, which was the rest mass energy density of the fluid that we're dealing with times the Lorentz factor. S is measuring essentially the momenta, I have a VI here missing. The momenta of our fluid, again with factors of omega square and factors also inside the enthalpy of the pressure to account for the fact that pressure is also able to add to momenta. And some quantity related to the energy of the fluid minus the rest mass energy density to account for what's left that hasn't already been taken into account by the D in some sense. So what we notice there is that because of our desire to write things in flux conservative form, and again, there were tons of reasons of why we wanted to do that, in particular, this having to deal with these kind of issues, we have to pay, however, a very dear price, which is the fact that we no longer deal or integrate the physical, what we would call physical variables. We no longer integrate the density of the fluid, the pressure, the pressure or the internal energy density, or the velocity of the fluid. We're integrating other things that are related to that. However, back and forth, we need them. So in particular, if I were to come in here, I see V. So that's part of our primitive variables. But then I see S, which has V hidden in it in some sense. So we need to have a scheme that goes back and forth. And this is a delicate one. Not when we go from primitive to conservative, this is an algebraic construction. But let's think suppose we have made a step where someone gave us the conservative variables, D, epsilon, and S, and tells us, okay, give me what the primitive variables are, just because I want to know what the fluid is doing. Well, immediately we have a problem because we don't have, remember, one thing that we also need to give is an equation of state, which is P is some function, say, of rho 0 and epsilon. So we have here a relation that we also need to invert, because inside the pressure we have density and energy density, rest mass density and energy density, that also come in here in a very nonlinear fashion. So unfortunately, this is where we actually kind of stop doing analytics and we have to do numerics. We're going to have to find roots somehow. So this one strategy could be the following. So let me just, I'm going to erase this here. So first, we're going to start with a guess of what the pressure is. So in general, we wouldn't know what that is, but say if we started, we would have started with physical values, rho p, so rho 0, epsilon, and v as our primitive variables. Out of these, we computed the conservative variables. With those, we iterated in time, and we have, say this is a level n, this is a level n plus 1 somehow. And so what we are here, what we could use for a guess, an initial guess for the pressure, is the pressure we had there, because we just took a step. If it changed, it didn't change by heck of a lot. And if it did change by a lot, maybe we're taking too big a step, we have two cores agreed, or the solution is already getting too inaccurate. So take an initial guess for the pressure. Then we know that the velocity of the fluid, the free velocity of the fluid, can be obtained by taking the ratio of this thing divided by rho h w squared. Right? So that's a trivial algebraic calculation. And in terms of the conservative variables, that's S, so that we would have energy, well, this curly E, D, and the pressure, and then we're using our guess here. So that allows us to get the V. Out of the V, we can get the W, right? So we can get W of P star, because it's just a Lorentz factor. So now I have V, P star, W, P star, and P star. Now I can take the ratio of D divided by W, so these are all P star, so these are D and P, now it's P star. So if I take D divided by W, the Lorentz factor which I already got, then I get rho 0. So now I have rho 0, V, P, W. The one that we're still missing is the energy density, this epsilon, not to be confused with this curly E. And this we can get from enthalpy, and we need to work out trying to just use what we know from the conservative variables or what we have already found from the primitive variables. So you can go through the algebra, and this epsilon is curly E plus D 1 minus W P star plus P star So straight algebra will give you that epsilon is given by this combination, where, of course, this means that epsilon also depends on this P star. So up to this point, I have, go back here, but I have rho of P star, epsilon of P star, and V of P star. But if I have rho and epsilon, these approximations, I can come in here and evaluate pressure. But generically, what's going to happen is that that pressure that we obtained with the rho star and the epsilon star we have computed is different from our P star, because we started with a guess. So then what we have is a residual, and then we have to iterate. So we would use, say, a Newton-Raphson scheme, and this is where the hard work goes. If we are very far from the solution, finding the root could be delicate. And this is what we were saying yesterday. It could truly be because of numerical errors that you cannot find this root. And at that point, what do you do? Well, that's when the black magic really starts, and different prescriptions will have to be applied. So this is what I was describing yesterday, or no, on Tuesday. So sometimes you fail, you go through all possible variables, and then you fail, and then you say, well, what I'm going to do, therefore, is to kind of relax my equation state, think of a simpler equation state, like I went from, and I from a polytropic equation state, I go to an ideal gas. Maybe I'll find a solution there. And if the number of places where I have to do those kind of things is small, then eventually the hope is that things are relaxed in the right way. And you can, of course, hope is never a good word. You have to work hard with another simulation, higher resolve, to see if now those problems get ameliorated. Of course, this is the simplest possible example. We're only done, well, not, oh, it's almost the simplest one. We've done special relativity, metric hasn't, curvature issues haven't come in. We have not yet assumed a particular equation state. Depending on the equation state we're dealing with, this may be more or less complicated. And as I said, the array, then there are either fallbacks. If you cannot get it with the true equation state, you cannot get it with an approximate equation state, then you can try and see if the points around the points where you're failing are well defined, in which case then you might want to fill that by interpolation of the nearest neighbors. So any question on this? So let's work out a little bit in detail example. So we're going to simplify our life a little bit more by making another approximation. So let's imagine we're thinking of a fluid that is relativistic, but it has such a high speed associated to it, but essentially all the energy that the fluid has is in kinetic energy. It's not in rest mass energy. So if that's the case, there are some shortcuts we can still take. We want to take that because that's going to allow us to write kind of in full detail in a way that would still keep us some sanity, the equations. So let's discuss about ultra-relativistic. Ultra-relativistic case. So suppose, where's my chalk? So in this case, our assumption would be that 0 times epsilon is much, much larger than rho 0. Remember, in our enthalpy, we have rho plus rho 0 epsilon. There's a rho 0 plus rho 0 epsilon. The first rho 0 we can throw away. If we can throw away that one, we can throw away a full equation. And what we're going to be throwing away is essentially the equation here. Because we're saying the energy of D is just completely irrelevant with respect to what's hidden in here once we have the epsilon. So the epsilon is, we have rho 0 times h. It's going to be rho 0 plus rho 0 epsilon plus p times doublet square. So this one is ignorable, so we can actually ignore this one. So let's go back to our equations. If we were not in the ultra-relativistic limit, remember our equations came from here. Sorry, rho 0. So under that assumption that rho 0 is irrelevant, then I'm going to change and define rho to be rho 0 epsilon, and rho 0, I'm going to throw it away. As it's so we combine rho 0 and epsilon, that becomes our physical thing. Another warning I would say is that this B we are free to put in the index up or down. And when you look at the formulations different people have written, they have made that choice. And that, of course, changes things in a very, at the analytical level, totally superfluous manner. At the level, it might change a little bit the equations and how you iterate them, or the conservative primitive transformation plays some role. It's not fundamental, but it's be mindful that you can check where the indices are before you pick up an equation. Okay, so that's our case. Let's throw that out because we don't care where the number of particles gets conserved or not, it doesn't matter, because the energy that will be lost or gained by particle creation or particle destruction is irrelevant with respect to the kinetic energy that the particles will have. Also, let's make a further assumption. Let's imagine that our fluid is such that, I mean, some people call it the slab symmetry. So we're going to assume that ddy and ddz are killing. So it's just going to be a 1 + 1 problem. So in that case, we can write the equations, and then this will be like dt, t. Let me just write it this way first. So if we look at this way, we already have our equations in flux conservative form, right? We have time derivative of something, the divergence of a vector in both cases, equal to 0. In fact, because of our last slab symmetry, the only thing that entered here is x, and this will be x. So that immediately tells us what we should perhaps choose for our conservative variables. So I'm going to define t to be tau. I'm going to choose slightly different variables because they are not exactly like ones we had there. They are very closely related, but let's define it this way. tx is s. And then txx, we can work out that is SB plus the pressure. Okay, so now we're going to walk through a little bit just to see one example of the things we have discussed, how they complicate when we have a truly rich problem. Because we were discussing the Berger equation, but that's too simple. Especially when we're thinking about jumps and eigenvectors, eigenvalues. That was just too trivial for us to comprehend all the intricacies of applying these techniques to deal with these kind of questions. So now let's try and follow kind of at least for what we have before. So we want to write an equation for our set of variables becomes a vector of unknowns, but we still have an equation of this form where Q and F are vectors. So let's recognize what those are. So Q is the vector tau and S. The flux is a vector given by SV plus P. And that's it. We don't have any source. We're going to describe later having perhaps something in the right-hand side that is not exactly 0. So it's not going to be true conservation form, it's only approximate conservation form. Okay, so we know what our next steps supposedly are, so let's work on them. So remember we had Q, T plus dx of f equal to 0, but we want to apply, let's say, a approximate solver. So we need to diagonalize this, or to linearize this. So it's going to be Q, T plus, now this is going to be d f d q dq dx. And then remember this will be playing the role of our matrix A. So what is that matrix A? Well, we're going to have to work, because what we have to do is just be mindful that if we define our variables as tau and s, we need the primitive to conservative and conservative to primitive. So the primitive to conservative is trivial. It's again another straightforward straightforward algebra calculation. So let me just express it here. Tau is rho plus p omega square minus p, and S is v w square tau plus p, where this v is the velocity in the x direction. That's the only place that we're allowing things to change. Coming back, however, we have the following relations. I need an equation state. Let's imagine our equation state is P gamma minus 1 times rho, sometimes called a polytrope equation state or an adiabatic equation state. So if someone gives us gamma, then we have a full description for P as a function of rho. And this equation state doesn't depend on epsilon anymore because we kind of lumped everything together. So now the conservative to primitive will be P is minus 2 beta tau So that's our conservative to primitive now. So if we have the primitives, go to conservative variables this way, and we come back that way. The neat thing is that in this case, because of a simple relation of our equation state, and because a simplified equation of motion, we don't have this iterative process that we described before. We can just straightforward get it, but it still is a much messier structure. But we're going to have to deal with that, because now we need to construct the matrix A, and the matrix A has derivatives of the flux. The derivative of the flux has sometimes our conservative variables shown explicitly. In others, they are shown implicitly because we have the primitive variables here. And we're taking derivatives with respect to our conservative variables to construct the matrix A. So the matrix A would be a 2x2 matrix where the following, with the following notation, let's say the following components, A1, A12 is 1, A21 is minus V squared, and these, I'm actually going to tell you, read the notes. They're kind of messy expressions which come out of going here, looking at the pressure, and we have them written down in terms of our conservative variables, so we just have to take those derivatives. So now we have our matrix. We know what other things we need. We need the eigenvalues and eigenvectors. So this is a 2x2 matrix. So it has two eigenvalues, which is 1/2. Well, formally will be A11 plus A22 plus minus A11 minus A22 squared. And the eigenvectors, okay, those are not too complicated. Sure. Okay, so here we are. We have essentially everything we need to compute. We have the eigenvalues, the eigenvectors. We have the equation of motion. We could just go ahead and apply the row solver. The one comment I wanted to make here, this should give you a pause, in that it very quickly got very messy, and we haven't even started. I mean, we don't have the most complicated system of equations or the most complicated scenario. So remember when I said before, if you have a problem where that techniques for defining value, that for problems that do show shocks and discontinuities could be applicable to any single problem. So if there was at any point that you say, well, I'm just going to learn that technique and not have to worry about the other ones, that should tell you you probably don't want to do that. Because if you're doing like Einstein's equations, just imagine doing shock treatments with Einstein's equations. It would be a mess. So we now understanding what type of equations we're dealing with and what sort of phenomenologies could be associated would prevent us working too hard if we don't have to. So in the case of equations of motions where the eigenvalues do not depend on the solution itself, then we can just go and make our lives a lot simpler. So in the notes, there is this exercise that you can go and try, code this all up. If you have coded, however, the Burger's equation problem in general, so an equation for a 1D, notice this essentially is just a continuation of the very same problem. If you have written modularly how to evaluate the fluxes, if you give it the right values, and you give it the eigenvalues, then it will spit out for you the fluxes, the approximations to the fluxes, then you can reuse all of these. And this is why we were saying already a few times that if you actually have the tools written down and the knowledge, more importantly, to deal with this equation or that equation, in generally, you're just going to keep applying over and over this one. You just have to make it sufficiently clean for you to kind of reuse much of what you've done before. So if you had done the Burger problem in the exercise and you didn't have any problem, you might consider going this way. It shouldn't be that much more complicated beyond quite a bit of extra garbage or baggage carried through to realize that now you have a problem in 2x2 as opposed to a one-dimensional problem, one variable problem. So any questions? So let's move to now general Tvc hydrodynamics. So we went from, yes? What is a matrix A? So the matrix A is remember, you start with this problem. And so this is a nonlinear problem. So how do you come up with a recipe to evaluate the flux in the right way? So these approximate Riemann problems rely on some sort of, well, by their name, some sort of approximation. The approximation we're making in the row solver is to say, well, turn these into this problem. And so this is a Jacobian to go into this way, and this matrix A is this one. It's a Jacobian matrix of your original flux. And so not only approximation and in the evaluating the matrix A, and then this becomes the problem you solve. Right? So remember, in row, you went from that one. Row says take the flux and try to write it in terms of some matrix A times Q. And that's what we're doing here. Yes. Oh, sorry, there was a second question. My bad.
How are you sure that A is, you need A to be diagonal?
Yeah. So the assumption was that that matrix had to be had to have a full set of eigenvectors, so it has to be diagonalizable. But beyond diagonalizable, it has to have all real eigenvalues. So how do we assure that? The flip side, if we don't have that, then we don't have a well-posed. We're not going to have a well-posed problem. So what our understanding is, if we're dealing with a physical problem, that has to be the case. Because you're absolutely right in that when you evaluate, I don't know, something like this in here, it could be that, again, you end up with these problems that you're actually taking the square root of 0, but numerically it happens to be slightly negative. And it will converge to 0, but how do you do that? Well, this is where you put tons of flags in your code every time, and this is a general suggestion. If you have to evaluate something in your code where potentially it could blow up or it could just give you a nonsensical answer, you should be mindful of that and have a way to react. At the very least to say, don't try to do this and tell me that something odd is going on. So here you will say, well, if it is negative, don't evaluate it because you don't want the code to crash. You might want to speed up a warning, this is going on. But if you understand that, so you could say, well, first, like what I would do, I would compute this independently, create a first step, and then I say, well, if it is sufficiently small but negative, turn it to 0. But it happens to be -3. Okay, I ended up in nonsense land, and I have to understand what the hell was going on. Similarly here, I'm dividing by this. If this is 0, I'm doing something that is wrong. But it could be that this minus that divided by that actually is both the numerator and the denominator are going to 0. And then if you take a L'Hopital argument, then it will go into 1. Again, you have to react to that. That's a problem where computers are dumb and they just follow your lead. And if you don't try to, if you're not kind of mindful of what you're going to do, they're just going to run there. And so you have to prevent these things. But yeah, absolutely. So our assumption is that analytically, all these has unique solutions and well-behaved, and then just to make it sure that you use that to your advantage and make sure you don't catch yourself into problems. Okay, so let's discuss a little bit on the general relativistic case. Okay, so the only difference now is we're going to throw in the metric. So to start with, our assumption would be that our fluid is described the same way. I mean, it has to, because it was nothing special here, except that, of course, now we are putting a metric there as opposed to the flat space metric. H is defined exactly the same way, say our enthalpy, because after all, this has no derivative. It's just scatter. I can always go to the local coordinates, which are flat, and I will be measuring exactly the same thing. So there shouldn't be any difference at this level. Our equations of motion now, we're going to have to deal with the fact that we have a curved spacetime. So our conservation of, say, of particle number becomes this. And the R1, of course, it's the same. Well, with the curve form. So what I'm going to give you is a quick way to get the general relativistic hydrodynamic. And then there is a more formal way, which also are included in the notes I gave you, which is actually they are taken from Miguel Alcubierre's book. It's very well described there. So why I'm just giving you those. So you should read that. If you have a more formal view, and I'll explain where and how. So, but the quick way is to first realize there are some simple ways to getting quickly to the equations as well as to realize that this one was the divergence of a vector. With respect to a coordinate system, this is just simply given by 1 over square root of your determinant, the A, of your vector. Right? So then you can multiply through by the square root of the determinant, that's gone. And this is telling us for free that we have an equation of motion for some variable in flux conserved form, right? Because this will be, well, let me just, maybe I could use 0. So that's in conservation from essentially the get-go. we're going to use that. So the only thing we might want to do is that U0 and UI are not necessarily the most natural quantities to carry through, because these are the components of a vector in our coordinates. But we might be thinking that geometrically that we have a foliation, and we want to define things that are associated with the foliation, where the velocity would be the 3 velocity in each individual slice, for instance. Similar things to what we did the other day, but let's try and introduce that. So the first thing is, if we have foliation, and that's a normal to the foliation, we can define, again, this factor, this Lorentz factor, by the product of the contraction of our normal with the fluid flow. Since NA is equal to minus alpha 0, 0, 0, right? And this is true because NA is normalized, and the metric in terms of the lapse and shift, the upstairs metric is. So since N has to be normalized to -1, then that's true. And so we get that W can be expressed in this form. It's alpha U0, where of course alpha is a shift. It's the lapse function. And we recall. So we're going to use these two to express our functions. We can now, that's a relationship between this lapse that we're measuring and the rate of change of the fluid time coordinate with the Lorentz factor. Now, we can try and obtain what the velocity would be associated to our observer that is not necessarily normal to the foliation, nor is necessarily flowing with the fluid flow. So let me just give you the expression, and we're going to recognize each term in there. So this one will be given by so suppose the following. Suppose you're an observer that has a different set of coordinates, and you're trying to say, what is the velocity that I see of the fluid? So I can take these UI coordinates that the fluid has, but they might be shifting. My coordinates may be shifting with respect to the fluid, so I have to react to that. So I'm adding this piece. Of course, the 3 velocity with respect to U is a ratio of UI to U0. So that would be what you would be measuring if you were not shifted with respect to these N observers. But now you add the shift because your coordinates may be different from slice to slice. And the last thing we need to add is this alpha, which tells us the difference between the coordinate associated to the foliation and the coordinates associated to the, say, this observer that has a different clock. So this is just to tell us that the proper times are different. So with that definition, we can, and of course, that we know the normalization of the, or that we're normalizing the fluid velocity as well, then we can derive that that thing actually is what we had expected. And so that prompts us to define the following. Oh, and one more thing. If we define, so in these slices, so if the lapse is the proper time between 2 slices as I go in the normal direction, I can decompose, and the shift tells us the difference between this label here and maybe this label here being exactly the same. So in addition to going to that way, I need to move to the left in this case. There is a relation of the determinant of intrinsic this hypersurface and the full of the space-time, which we're calling G, which is the following: the square root of minus G is equal to alpha times the square root of H, gamma. This is the intrinsic metric to the hypersurface, which we can obtain by simple projections of the full metric. I'm not sure how many of you know that, but if you're not, don't worry. So the intrinsic metric of the hypersurface is related to the full metric in the following way. Let me just write it where? I'll write it here. So GAB dxa dxp is equal to minus beta right. So if I take t equal constant in the foliation, that would be a single member of that leaf. This is not playing a role. So distances of points that are separated by a constant time, by the same time, sorry, it's just measured by gamma ij. And once we go off, we involve events that have different coordinate times, then the distances either can be taken using this expression or taking the full metric. And this is a relation between the metric, the full metric, and this 3+1 representation. So if we use this, we can prove that this is true. So now we can use all these relations to re-express that, and immediately we realize that the following, just as before, is a convenient variable. So ρ0 times w allow us to rewrite the equations of motion, this one, in the following way. So it looks a little bit longer and perhaps not as clean as this one, but that's because we're insistent in carrying variables that are related to the physics of the fluid. And this v here is the velocity, the free velocity of the fluid that we'll be assigning, given our coordinates. And this shift is to account for the fact that our coordinates keep shifting with respect to, say, the normal coordinates. The other thing we notice here is that we have a 3-volume element. This, again, it tells us that once we try to measure how much energy we have in a little volume, as it changes, as we go from one slice to the other one, because the volume is changing as well, then that has to be reflected in here. So that's that. But beyond that, by and large, we have exactly the same thing. In fact, depending on the authors and the papers you look at, some cases, this variable d and all the conserved variables get the volume element, or the 3-volume element, absorbed into them. So sometimes people call d this way and d twill the same with the multiplied by the square root of gamma. It's just a convenience in the presentation. So this is not very difficult. So now, for the other one, so we have only taken care of this one. Let's look at this one. So we cannot use such a simple expression, which of the covariant derivative of a vector, the covariant divergence of a vector, but there is almost a similar one for this one. It's the divergence of a tensor given by the following. Where did I put it? So now we can use that expression to obtain the expressions for associated to the conservation of energy and momentum density. So let me do it this way. By introducing first some definition. Let me just call CSA, just as before. Now is where writing the indices up and down might actually come in handy, because if I write this one this way, right, the metric with one index up and one index down is just a identity. Yes. Yes, it has to be. Yeah. So we introduce this quantity, and then we observe, after introducing this quantity, we have this relation. And with that, and using this identity, we can write the following. So let me just write first, and then let's comment on what we get. Okay, so there what we did is we took this identity, which we obtained when we expand that piece over there, the conservation of stress energy tensor. We introduce this expression, which is, again, very much like the one we used before. We plug that in here, and we just expand using this relation and these relations. Once you do that, you end up with this, and immediately we are kind of disappointed, because we don't have a zero on the right-hand side. Right? We have something where we end up with a contribution that is non-zero. So this equation will not have conservation form. I mean, we'll have conservation form, but it's not going to be conserved. We don't have a zero here. We have a source. So this is going to be something we're going to have to deal with, approximately. Then this piece, notice that we have the delta. If you actually check different sources of literature, sometimes this is not true. People choose to evolve with the index up. And if we do that, you're picking up a metric component here as well, which you're going to have to carry through. If we're using with the index down, and you happen to use a Cartesian representation of your metric, then this is just a trivial addition. You don't have to take many contributions there. But either way, this now becomes the flux. This is the conservative variable that you're integrating. Again, you could absorb the volume element in the S or not, but that's a matter of choice. And you have to do this. So what do we do when we have a source, which we haven't discussed yet? So let's go back to what we discussed at the very beginning today. So we have this equation. But now let's imagine we have a source. How do we kind of obtain at least a formal representation how we were going to integrate the equations? We integrated by dt dx, right? The whole thing. So we carry the integration all the way to the source. So if we were to write our approximation, this will turn out to be so we want delta t times the source evaluated at the midpoint, at the center of the cell. Let's see. I think that's right. So this is our second equation. And we're missing a third, which is the one for the energy. So again, we define the new variable epsilon to be rho h omega squared minus p minus d. And we take not the spatial component here, but the time component. The spatial component gave us that one, the time component, we put b or t there. Then the equation of the motion will come from here. And then, well, using all our variables, we can end up writing this in the following way. Which again is an equation that has now a source, and we're going to have to deal with it in the same way. But as far as the flux is concerned, well, we have again the of a flux, and we would do the same work as we did before, except that now our equation has now complicated our system of equations. We have 5, and so we have to deal with a 5 by 5 matrix. The eigenvalues, eigenvector calculation become a mess. And that's when, depending on who is working on a particular problem, you may have other solvers which do not involve using all the eigenvalues and eigenvectors because it becomes quite cumbersome. But that we haven't discussed. But I would suggest you, I mean, in LevX book you have tons. But or if you have questions, ask me later. I can point you in the right direction. The thing I wanted to mention is that if you show this equation to someone who is a formal relativist, you're going to give him or her a heart attack because they are ugly as hell. In particular, we're carrying through like partial derivatives when maybe we could have done a better job. You would have said, well, the true way of writing this in covariant form would have been to have at least space derivatives here, the covariant derivatives associated to the matrix gamma ij, and indeed those exist. They can be done, but I think that might confuse a lot of people. The notes are posted in the web page, or the equations are everywhere. There's a very beautiful way of doing obtaining these equations by coming in here and doing projections. So if you project this equation along the n direction, then you obtain the analog of the energy equation in covariant form in a much simpler way once you relate the covariant derivative of the full spacetime with the covariant derivative of 3 plus 1 of the 3 slice. And then if you're projecting the direction that is orthogonal, HC, which is orthogonal to n, then you obtain the equations of motion for the momenta. So if anyone is interested, we can talk about that later, but I don't think we want to go here for everyone, given the different directions we are coming from. So now, how would you go about implementing these equations? Again, you would use If you're doing in this dynamical spacetime, something like what we have shown in different movies, so you'll have a module, let's say. Suppose you have written down a code that solves Einstein's equations for you in vacuum. The fact that they are decoupled formally from the point of view of what the principal directions are and how they influence each other, we argue the other day that they are not coupled at the level of the principal part. So you could imagine writing the Hydra code independently, assuming that someone gives you the metric. You can imagine you've written a GR code, assuming there is a source that someone gives it to you, and then you just couple the two codes. So what would happen if you try to do that? Actually, not much, because of the way we are iterating the equations, or typically iterating the equations. We typically are doing explicit iteration. So let me imagine you have something at level n. So at the level n, you may have the variables for the metric. Let's call them curl G. So here is everything that goes into iterate this one. And here you have the variables for the fluid. Let me call it F. Call them F. And so if you had written this code using, let's say, a row solver or whatever, you know how to go from here to there. And if you've written your Einstein equations in vacuum, you go from here to there on this front. But also you know that the equations of motion for this one, which are iterating, have these guys undifferentiated. And with respect to this one, you have the equation of motion for the fluid, have these ones at most differentiated ones. That means you have in here all the information you need to evaluate the source of each other with the information coming from the fluid and the metric at that level. So now you take a step, and this step could be a full step or could be an intermediate step of Runge-Kutta. So you have to make sure that if I'm doing that step, I evolve this one with sources provided by the fluid. I evolve this one with sources provided by the metric sources, and more than that, right? So the fluxes are modified by the appropriate volume elements, etc. Now let's say this is an intermediate Runge-Kutta. You have to make sure that you advance both to the same level without taking the next step. So if you have done it Runge-Kutta, let's say you know that you take a half step, then you take another step. But when you take the other step, you actually are using values that you just obtained at this intermediate level. And if you haven't advanced the fluid to that intermediate level, you cannot take the next step because you wouldn't be evaluating the right-hand side with all the information you need. Is that clear? So, but beyond that, that's pretty much to it. So typically, codes have been written. Our codes have been written in such a, this was written first, this is second, and then this one only asks from this one, just give me the full metric. Whatever it is, I'm just going to use it in this form. I have all the information, I take the step, and vice versa. The metric, the Einstein equations part, asks from the fluid enough to evaluate the source, which is a simple evaluation, and then you keep going to the future. And this is again where the iteration and all the messy thing, all the inner engine of the fluids iteration is just here. We never use it here because we can make it much more efficient on this side. So I'm going to stop here. Tomorrow we're going to discuss a little bit of, this is for this fluid, this is as easy as they get. Remember, what I haven't told you here is what is the equation of state. You could imagine using an equation of state that is almost the one that we discussed before, like this adiabatic law index of equation, something like so. Still, you'll have to, because the equations are sufficiently complicated, it involves some Newton-Raphson, some root finding to try and obtain the transformation from conservative to primitive. But it could be a lot worse. This could be a tabulated equation of state coming from nuclear physics. This is the kind of things that Daniel was showing the other day. Those are needed explicitly because these reactions have to be taken into account. In which case, the conservative to primitive becomes much more complicated. Now you have to search on a table. There is not a simple analytical expression that links pressure to density and internal energy or temperature. So things can get much more complicated. We also have not discussed so far when I write here, any further contribution to the stationary tensor, but we already show you several examples where magnetic fields can play a fundamental role, so there is an addition to that. And this addition will also have its own equations of motion. You have to understand those equations of motion and how to integrate to the future. So I'll describe, in general, some of these things tomorrow, and then maybe take it to some other directions. But I'll stop here, and if you have any questions, shoot. Thank you. No questions? Okay.